Can you hear me? Yes. Good. So the Frontiers of Science series started, as Tracy just mentioned, when I arrived at Penn State to assume the Eberly Chair in Physics. And I've been held each year for the last 3 decades, making it one of the most successful outreach events in central Pennsylvania. The series has brought to us lectures on the big questions that humanity faces. For example, is there life on other planets? On becoming human? Predicting future? The AI revolution? And Einstein's universe. They bring out the underlying unity of knowledge or consilience. And I think that really, to me, is exciting foundational thing about these lectures, consilience. So let me say a few words about how it all started. Thank you. I can do it. So how it all started. The first series of lectures was on cosmology given by Robin Tully. This is a picture of his today, not 30 years ago. 30 years ago, he was a young postdoc. He was one of the postdocs at the Institute of Gravitational Cosmos. And through his lectures, Robin developed a strong group of fans. He would be, for example, at Wegmans or in the corner room, just quietly, trying to quietly have his lunch. But then people would surround him and keep asking him questions about the lectures. That gave us a first-hand feel for the enthusiasm that the community has for big questions. And the Frontiers lectures became an annual series. Robin went on to a very distinguished career as a head of R&D, designing, of all things, race cars and motorcycle engines. His experience here was in astrophysics and cosmology, and he was the chief scientist at Renault, Mercedes-Benz, and Bentley. In 2019, he founded Physics X and serves as its co-CEO. He is dedicated to building deep learning and simulation solutions to unlock the breakthrough discoveries in engineering. But throughout the 3 decades of his career moves involving diverse research, he has kept in his office the framed program of the first Frontiers of Science lectures that he gave. It is still in his office in England. And also he is really a living example of consilience. I'm truly delighted that year after year, the series has brought to Penn State hundreds of people in spite of challenging winter. And I'm proud to belong to this State College area community, which has so many people interested in how fundamental science enlightens us and also impacts our daily lives. One of my fondest memories is the picture that you see here. It is from a 2019 photograph. And it is really by the Nobel laureate Barry Barish and a student from elementary school in State College. After the lecture, she came up to him to ask him some questions. And Barry spent more than 5 minutes patiently answering all the questions with the same seriousness that he shows when he answers questions of his esteemed colleagues. And I really felt it was really moving. And I had this picture taken, and it is one of my fondest memories of these lectures. And of course, in addition to inspiring these young future scientists, the lecture series also has been very instrumental in informing the older community in terms of the developments at the very frontiers of science. Now, this series could go on successfully for a quarter of a century because of strong and continued support from the Eberly College of Science deans, starting with Greg Joffrey, then Howard Groch, then Dan Larson, Doug Cohen, and now, of course, Tracy. And as Tracy mentioned, during the first 25 years, Barbara Kennedy was a priming force behind this lecture series. And now we are very fortunate to have Heather Robbins and the Communication Office, which continues this tradition with meticulous care. Thank you all. Let me now turn to today's lecture. And our contemporary understanding of physical universe that we inhabit especially at a large scale, is based on Einstein's theory of general relativity. I have been working on it for about 50 years now, and it is truly a marvelous theory, rightly held as perhaps the greatest creations of the human mind. My talk in this series in 2004 was on the nature of space and time in general relativity, basically how general relativity brought about a revolution in our understanding of space and time and its consequences. Soon after it was discovered, Hermann Weyl, a world-renowned physicist and mathematician, expressed his admiration in the following words: "It is as if a wall that separated us from the truth has collapsed. Wider expanses and greater depths are now exposed to the searching eye of knowledge, regions of which we had not even a presentiment, we had not even dreamed of." There is about general relativity, I think the best way to illustrate its beauty, its serenity, its multiple strengths is really through the words of the famous sculptor Henry Moore, whose creation, the atomic energy, graces the University of Chicago campus. And he was asked by the Nobel laureate S. Chandrasekhar how one should view sculptures, from near or far. And Moore replied, "The greatest sculptures, like Michelangelo's La Pieta that you see there, can be viewed, and indeed should be viewed, from all distances, because new aspects of beauty will be revealed at every scale." And that is absolutely true about general relativity. For people like me who study it in detail, year after year, we find new aspects of beauty, new aspects of depth, new aspects of the supremacy of human thought that are emerging out of the theory, and new discoveries are being made up here. The talk today will explore two aspects of this theory that have witnessed astonishing progress over the last 2 decades: black holes and gravitational waves. They are both manifestations of the deepest aspects of this theory of general relativity of Einstein's. They're quite different, but beautifully intertwined. It just happens that the most recent paper that I wrote, in fact, it's not yet published, it will be in the journal about 2 weeks from now, it explores a certain manner in which these two aspects emerge from the same common framework. They are diverse manifestations of the geometrical structures that underlie general relativity. And just after completing this research, I was taking a walk. And by a walk, I usually listen to some classical music. And I happened to listen to Bach and one of his fugues. And I realized that what we had discovered in this paper was an analog of a musical fugue. There is a common mathematical theme that serves as the first voice of our paper, providing the theme and the subject. And black holes and gravitational waves develop it in a contrapuntal manner, just as in a fugue. And this is another manifestation of unity of knowledge, consilience. Our speaker today is Professor Gabriela González, who was on, as Tracy mentioned, was on the Penn State faculty from 2000. I thought it was 1997 or 1997 to 2001. And then she moved to LSU, where she is the Boyd Professor of Physics and Astronomy. In 1915, when LIGO, the collaboration, which has over 1,000 scientists and engineers working on it, discovered or detected gravitational waves directly on Earth, Gabriela was a spokesperson of the collaboration. And since then, the area has truly blossomed and now plays a prominent role on the forefronts of physics and astronomy. Not surprisingly, Gabriela has been literally showered with prizes and honors. If you visit her office, it's very, very impressive to see. It's almost completely covered by these mementos of various prizes and awards that she has won. She's a member, as Tracy mentioned, is a member of the US and Argentinian Academy of Sciences and also a fellow of the US Academy of Sciences. My personal association with Gabriela goes back to the early 90s when she came to the US to do a PhD under my supervision. We quickly completed 2 projects and then she moved on to experimental gravity. It has been a true joy for me to watch her over these last 3 decades to blossom into one of the leading scientists in gravitational wave physics worldwide. And it is really kind of a feeling of joy and a feeling of fulfillment that I get by looking at her evolution as a scientist. Gabi, it's all yours.
Thank you, Rai. And it's true, we have a very long history together and we've learned so much from you. So thank you for that introduction. So I want to tell you today about the discovery of gravitational waves and the latest news, because this is just the beginning, even though we started many, many, many years ago. Yeah, there we are. Okay. So I want to tell you about gravitational waves, and this is what the first one looked like, produced by black holes that were predicted by Einstein's theory. And from his theory to this discovery, 100 years went by. But from this discovery to the more than 100 discoveries we have now, there's been less than a decade. It's been amazing, an amazing story. And like I say, this started with Einstein's, and Einstein's theory mathematically is very, very complicated. And that's not the reason why I changed from theory to experiment, but I did learn general relativity when I was a graduate student, even an undergraduate student in Argentina, which is where I am from. And many of you might remember Newton's law of gravity. Do you? I hope so. We learn it in school. We don't use it very often, but you might remember that Newton's theory is the one that explains why objects fall to the earth, sometimes when we trip, but also, and that's why it's so beautiful, it's a universal theory because it explains things around us, and it explains why the earth goes around the sun and why the planets go around each other, and that's because of the law of gravity. And Newton's theory says that law says that all masses attract each other. There is a force that attracts them, and that's what makes things go around each other in space, in orbit, in elliptical orbits or circular orbits. Einstein's theory was conceptually completely different. His objection to Newton's theory is that that force had to travel immediately, and that meant faster than the speed of light. And in 1905, he had come up with another theory, the special theory of relativity, that had a universal speed limit, and that was the speed of light. Nothing could travel faster than the speed of light, but gravity was, Newton's gravity was. So he came up with this theory in which masses would interact with space-time. And the way I like to think about space-time is like a grid paper. You remember when you use grid paper to draw squares and all the points in a grid paper have equal distances? Now think about that in 3 dimensions. That's space. Now think about clocks in every corner. That's time. That's space-time. And if all the distances are the same and all the clocks are synchronized, we call that flat space-time. But if there is a mass, and that's what Einstein said, if there is a mass in the space-time, then it will curve the space-time. And then clocks are not going to run at the same rate here here than there, and distances are going to be different near the mass and farther than the mass. That's a theory, and it can be explained, like I said, the theory, the math is very complicated, but conceptually, the theory is just beautiful. And something that the theory predicts, just like Newton, and let me pause this for a second, is that the Earth goes around the sun. It's good that it predicts things that Newton predicted too. It actually predicted Mercury's orbit just a bit better, and that was something that had intrigued people about Newton's theory, and he solved that. But the theory had a lot of other consequences, like light not traveling straight. Light would bend around the sun and other masses, and that was the first experimental proof of Einstein's theory. But like I said, it also predicts that if we have two masses, they are going to orbit around each other. Now, according to Newton, if we only have two masses orbiting around each other, then they are going to do that forever. According to Einstein, because the masses are curving the space-time, and because the masses are moving, the space-time has these little ripples, these little curvatures, and those are gravitational waves. And those gravitational waves are carrying energy away from the system. So the two masses are going to get closer and closer to each other. And if we think about black holes, then there's nothing else than the mass of the black holes and the space-time. We don't have to worry about nuclear physics in neutron stars or any other dirty effects, as we sometimes, as theorists sometimes call that kind of physics. If we have black holes, then we, and not we with pencils and paper, but computers, people in numerical relativity, can calculate what is going to be the features of those gravitational waves. And this is what the wave is going to look like. Now, what is this wave of? We call it gravitational wave, but what does it mean? So the wave is produced near the black holes. It's traveling at the speed of light, carrying energy away, but what is it doing? The way I like to think about it is that if the wave, and there are waves going through Earth now as we speak, there are waves, now we know that there are waves produced all the time, and they are going through Earth because we have detected many of them already. And what they are doing is changing distances, changing space-time. And it's a wave. A wave means that things go like this, right? So that's what distances do. They get shorter and longer, shorter and longer. And that's a distance between free masses, distances on objects that, of course, interact with the matter in the object. But if we think about things floating in space-time, then that's what the distance between the objects would do. Now, one prediction of Einstein's theory, which is difficult to believe, but it is true, the math tells us so, is that the amplitude of the gravitational wave is proportional to the distance that we measure. So if we measure a distance between two of us, again, floating in space, so it's only affected by the gravitational wave, then that distance would get longer proportional to the distance between us. The farther away we are, the larger the change in distance. So this is, like I said, what the distances here on Earth would change from these two black holes moving around each other. And this is a numerical calculation, so it's, you can believe it, using Einstein's theory, using all the math of Einstein's theory. And because the black holes are getting closer to each other, they are moving faster and faster. Newton already tells us that. The closer they are, then the faster they move. So that means that the wave, the gravitational wave, it's going to grow larger in amplitude because they're moving faster, but also shorter in period because, again, the orbital motion is faster. And here the movie slows down. The black holes are actually moving faster and faster. Here the move is slowing down, but at the very end, the black holes get so close that they merge with each other. And when they merge, they form a single black hole that after a little ring down, it keeps rotating, but it's a completely spherical object. And again, according to Einstein's theory, that rotating object does not produce gravitational waves anymore. The theory says that a system or an object that produces gravitational waves needs to have some asymmetry. We call that mass quadrupole, but let's call it asymmetry. So I am producing gravitational waves here, although my husband who works in quantum gravity says I cannot because I cannot produce a single graviton, but classically, any object that has asymmetry, that has this quadrupole, would produce gravitational waves. And that was a system of the two black holes orbiting around each other, but a single black hole does not produce gravitational waves. So that is a beautiful waveform, and it looks easy to detect, right? We just need to measure distances that change like that. The problem is that, and Einstein himself realized that in 1916, just less than a year after he published a theory of general relativity, he published a paper with several mistakes, because every scientist, well, I don't know if every scientist, I don't know about the Bible, but every scientist makes mistakes, and Einstein did too. So that paper talked about gravitational waves in 1916. But when you put the constants in there, there's a constant of, there's Newton's constant because it's a theory of gravity. There's a speed of light because it's a relativistic theory of gravity. And that means that this amplitude is very, very small, unless you have big masses moving really, really fast. So that wouldn't happen on Earth. It doesn't happen very often in space, except when you have this kind of violent astrophysical events, when you have black holes or neutron stars, which are the most compact of stars and then can get very close together, moving really, really fast. But even for those objects, this amplitude, like I said, it's a fractional change in length. It's, what would you say it's small? Part in a million is small, right? Part in a billion, it's smaller. Part in a billion, it's 1 part in 10 to the 9. A part in a trillion would be a part in 10 to the 12. These are a part in 10 to the 21. Really, really, really small. So that's like comparing atomic dimensions to the distance between the Earth and the Sun. So would you say that we can measure that? Well, Einstein didn't think about that anymore. It was too small. Most scientists, in fact, there was a whole discussion for decades on whether gravitational waves really carried energy, whether they were a mathematical artifact or not. But then even when they're not, can they be measured? Can we really measure that kind of precision? And well, humans said, if we can do it, we should. And that's what we did. So what we are using is interferometers. And you might or might not have seen interferometers, but let me explain them roughly how they work. We have a beam splitter, a laser. A beam splitter splits a beam in two. A laser is an electromagnetic wave. And then we bounce them on mirrors, and then the two waves come here, and then this wave will split in two, so half will go here, and this wave will split in two, so half will come here. So the two that come out of here, if these two distances are the same, then these two waves are going to cancel each other. So there is no light coming out of the interferometer. But if the distances are changing with respect to each other, then the light doesn't cancel anymore. And if we put a photodiode in here, instead of seeing dark, we see some light. And then we see no light, some light, no light, some light. So by putting a photodiode in here, we can measure the difference in distance between these two arms of the interferometer. That's called interferometry. It's used in many, many precision experiments. And I was telling you that gravitational waves change distances like that because it's a wave. It also changes distances. If the wave is traveling through Earth like that, then it will change these distances. When these distances get shorter, these get longer. When this gets shorter, that gets longer. And that's exactly what this interferometer is measuring, because it's measuring the difference in distance between this and that. But now again, we want to measure this with a precision of a part in 10 to the 21. We don't even have a name for that, and if we had a name, it wouldn't matter, but we have to imagine how small that is. And we've done that. The first thing we did is, and by we, I mean you have all done this, because this has been facilities built by the National Science Foundation with your tax money. So we thank you all for this. The National Science Foundation built 2 observatories, one in Livingston, Louisiana, and another in Hanford, Washington. And the first thing that was needed is a very long arm, because remember, the longer the baseline, the larger the change in distance, the easier it is to measure. So it's 4 kilometers. Now, I know people are not used to SI units or metric units. 4 kilometers is 2.5 miles. 2.5 miles. It's not just a short walk. It's a few minutes drive. So we have 4 kilometer arms. We have a beam splitter in this building, a laser in this building, and then it goes back and forth in these arms. But we still need to measure a part in 10 to the 21. A part in 10 to the 21 of 4 kilometers is 10 to the minus 18 meters. And I'm not going to ask you to remember what kind of objects are that small, but I'll tell you that a proton is 10 to the minus 15 meters. So 10 to the minus 18 meter is a part in 1,000 of a proton diameter. So we are measuring, and we are, as I speak, we have detectors that are measuring this 2.5 miles minus this 2.5 miles with the precision of a part in 1,000 of a proton diameter. And we do that, and that's we humans, engineers, physicists, putting concepts to work. So let me tell you a bit more about how we do that. That's a simplified picture, a Michelson, as we call it, a Michelson interferometer. But the mirrors, well, first the laser has to travel in vacuum, because if it travels in air, especially in weather like this, but in any weather, the laser would not travel straight, and then the differences in distances we would be measuring are not produced by gravitational waves, but by weather or air. So we make the laser travel in vacuum. This is one of the largest vacuum systems in the world. And these are not small vacuum tubes. They are like 1.2 meters in diameter, and they are 2.5 miles long. This is vacuum engineering at its maximum. The laser, and especially we are now since 2010, we are in a second generation of detectors, and the laser is a powerful and very precise laser that was produced with the help of the Max Planck Institute in Germany. It's a very specialized laser. The mirrors are not mirrors bolted to optical tables. They are mirrors that ideally we would like them floating in space. But of course, these have to be mirrors that are very carefully polished, very special substrates. So you cannot let them go because they will crash. So what we do is we hang them in pendulums. And if you hang them in pendulums, you say, well, they're not free anymore, right? They are actually free in the horizontal direction. They are not free in the vertical direction. But what we want to measure is changes of horizontal distances. So pendulums work for several different reasons. And a pendulum is actually also a way to isolate the mass from the motion of the ground. If you hang a pendulum, and I usually carry a pendulum with me, but I forgot it today, I'm sorry. But you can imagine if with a yo-yo, instead of making it go up and down, let's think about trying it as a pendulum. If you try it as a pendulum, and then you move the top slowly, the bottom, the mass, it's just going to follow. So we are not isolating. The mass is going to be moving in the horizontal direction just as much as the ground. The gravitational waves we want to measure, the precision I mentioned, is precision at certain frequencies, at higher frequencies, like 100 hertz, 100 cycles per second. But when you move the top very fast, what does the mass do? Have you ever tried this experiment? If you move the top very fast, this mass, it's going to move a little bit, a lot less than the top, as long as you do it fast. There is a special frequency, you might remember, it's called the resonance frequency, at which if you move it like that, the pendulum is going to move a lot more. And that's, for a pendulum about this long, is about 1 cycle per second, 1 hertz. So at 100 hertz, the ground might be moving, but this pendulum is going to be moving a lot less. We call that seismic isolation. And we do that 4 times. We have this pendulum hanging from this, hanging from that, hanging from that. That's a quadruple pendulum. And that's not enough. We have that hanging from a platform that has 3 layers where we have sensors that measure the relative motion and then cancel it. We call that active seismic isolation. And all of that, this is the active seismic isolation, that's a quadruple pendulum. All of that is hanging from, it's hanging inside a vacuum chamber. So it's all in vacuum. So you have to build it really, really carefully and then put it and close the chamber and pump down the vacuum, and then you don't see anything from the outside. It looks like that. And this is a beam splitter, and you would say, well, if the other 2 masses are there, that means that they are very close. That's not a 4-kilometer long interferometer. And that's because we play a lot of tricks, a lot of optics tricks to make this work. We make the light go back and forth. So this is like I was saying, the beam splitter, and these are the other 2, but these are these mirrors that are making the light go back and forth between the mirror at the very end and this one. And we need to keep pushing these masses so that the light goes back and forth with constructive interference. And then that means that we keep it so that the light coming out has destructive interference, like I was showing in the previous movie. So that means that the light going back has constructive interference. We don't let that light go to waste. We put another mirror in here to make it go back. We call that power recycling. We do that, and then we have the output. We make it go back with a signal recycling mirror, and we don't end there. Lately, in the last several years, instead of measuring vacuum, as we call it, because the interference is destructive, so in principle, we're measuring differences from vacuum. The quantum vacuum is noisy, and we make it less noisy by doing something vacuum squeezing. So we squeeze the noise to make it smaller. I'm not going to go into details of that because it's another hour talk. But this shows you how much engineering, how much optical and mechanical and electrical engineering, as well as physics and time had to go back in, had to go into making these detectors work. The concepts were created in the 70s. The first prototypes were tried in the 80s. The facilities were built in the 90s. But you really need a lot of people to make this work. And all of that to get at the output, at the photodiode, a noisy signal. And that's what we look for gravitational waves. And that noisy signal, if you look at it, even at low frequencies, the largest motion is 10 to the minus 18 meters. But we are looking for things very small in there. And all of this is done by a lot of people. The LIGO laboratory is managed by Caltech and MIT. They were the institutions that started this, but there is an international LIGO scientific collaboration with lots of institutions, including Penn State, and there it is. And Penn State has been part of this institution since 1997, when the collaboration was founded. 1997. And this all led to the discovery of gravitational waves in 2015. That was a lot of years after 1997, after the first concepts in 1970. Some experiments take a lot of time. And let me tell you about this, because you might say, well, that's just a noisy graph, but to me, it still moves me. What I'm showing here is in blue, the signal on that photodiode at Livingston. So what we are seeing is more light, less light, more light, less light. And that's noise. And we usually see that. And the signal in orange, the curve in orange, is the same the light on the same, on a different photodiode, but in a photodiode 3,000 kilometers away, that's showing also more light, less light, more light, less light, but not the same as in Livingston. These two don't seem to be correlated. But on this day, September 14, 2015, very early in the morning, it was like 5:30 a.m. at Livingston in Louisiana, there is something that looks like a sine wave. And it looks like a sine wave that's growing in amplitude and in frequency. This time is shorter than this one, and this one is shorter than this one. So it's increasing in frequency, it's increasing in magnitude, and then it goes away. This was amazing. We were preparing, we had finished the installation of the second generation of detectors. We had operated the first generation as a proof of principle. We were testing this second generation, and we had decided, well, we don't have the sensitivity we want because it takes years to get there, but let's practice taking data. So we were going to begin taking data as a proof of principle again for a few months to test our detection algorithms, and we saw this. We could not believe it. Literally, in the beginning, we all thought that somebody was playing with us, that somebody had injected this signal, because we do injections all the time to test our system. So we said, well, who did that? Who gave permission to do that? And I was a spokesperson, so I should know. I was ready to kill somebody, but it wasn't. It wasn't a hoax. It wasn't a test. It was real. It took us several months to prove it. And again, look at this. Look at how, despite the noise, you can see these two photodiodes 3,000 kilometers away showing the same thing. It was magic. And from this, it was not only magic, it was incredible, because from the frequency, we can measure the masses of these systems. And at the time, and this is not a secret, but it's something we don't say very often, is that the only guaranteed source we had for these detectors were mergers of neutron stars. Because now we all talk about mergers of black holes, and everybody knew that black holes existed. Astronomers had measured X-rays emitted by matter falling into black holes. So black holes were known to exist, but nobody had seen a pair of black holes because, well, then there is no matter to see. There are no X-rays. So nobody had seen a binary black hole system. But there are several neutron star binary systems in the galaxy. They are going to take millions of years, hundreds of millions of years to merge, so we're not going to wait for those in our galaxy, but because we can see signals from many other galaxies, we could wait for those. Those were the target. But from this frequency, we could tell that these were not neutron stars. These were masses that had 30 times the mass of the sun. Neutron stars have about 1.5, 1.3, 1.4 times the mass of the sun. These were big black holes, and I say big because from X-rays, people had seen black holes that were around 10 or 20 solar masses as maximum. And here there were two black holes, not just one, orbiting around each other, and each one was 30 times the mass of the sun. So this was just incredible. It took us several months to convince ourselves that this was not a hoax, that this was consistent. These were really black holes. We don't know what produced those black holes, but they were black holes, they were masses, and we knew they were black holes because we knew how close they got, so we could have a sense of the size and the mass from the frequency. So it took us several months from September 2015 until February 2016, until we could say, we did it, we really did it. And it took, like I say, the work of hundreds of people doing this validation. There were only 4 of us on stage, Ray Wise and Kip Thorne, who in the 70s had begun proposing this experiment. So they are the older ones of the five of us. Dave Wrightsey was and still is the executive director of the LIGO laboratory. I was then the spokesperson of the LIGO collaboration. So I was representing the collaboration, and Franz Cordova was there. She was the director of the National Science Foundation celebrating this discovery. So this was a press conference in 2016, and it was a cover of all the magazines and newspapers that the next day. But the one thing that I really like about this, and this was just a coincidence, we didn't plan it, but the year before, in 2015, the United Nations had not worried about gravitational waves. They were discussing women and girls in science. And in 2015, they decided that every year on February 11, they were going to celebrate the International Day of Women and Girls in Science. And that was the day we were announcing this discovery with 2 women scientists among the 5 there on stage, which sadly, it's not the percentage of women in physics or astronomy. It's a lot lower, but there we were. And it was such a happy coincidence that I still celebrate it every February 11.
And both women were faculty at Penn State.
That's right, yes. Franz Cordova had been a faculty in the astronomy department at Penn State. Yes. So this I like to call the music of the universe. And music because it's a wave, and we can represent the wave as a time series like here, or as a color plot. This is a color plot where we have time in here. Notice that this is a fraction of a second, and this is frequency. So it increases in frequency, so it goes like that. It increases in amplitude, so the color represents the amplitude. This is the time frequency diagram of the signal in Livingston. This is the one in Hanford. But we can also put this on a speaker, right? We can digitize, we all digitize, listen to digital music now. So you can put any wave on a speaker and see what it sounds like. And we wanted to do that. We did that all the time with the noise, but we wanted to do it with this. And let me show you what it sounds. Did you hear it? Doesn't sound very nice, I have to admit. We did it, but let me show you again. It's played twice, so you have to listen carefully to hear it. There's a thump in there. That's about it. We didn't like it. So we said, well, you know, astronomers paint the ultraviolet sky in blue, the infrared sky in red. So let's add 400 hertz to this wave. We can do that. And then this is what it sounds like. A lot nicer. That's a real one. This is the adapted one. We still like it. We actually, I danced to this music. We were so happy with this. We have this wave in t-shirts, in dresses. And we actually have published, and I say we because it's me with other authors, including my husband, published 2 books that are called, use this theme, The Sounds of the Cosmos in English, and in Spanish, La Música del Universo. So these don't have any formulas. They don't have any math. And this one especially has a lot of history of the field if you want to read about it. Anyway, as Abai mentioned, in 2017, there was a Nobel Prize for this discovery. It was for Ray Weiss from MIT, Kip Thorne from Caltech. They were the pioneers of this field. Barry Barish, who had been an executive director, starting not at the beginning, but when times had gotten very difficult for LIGO, so he was the one who made it flourish and progress. But what we were so happy about this announcement is that in the press release of the Nobel Foundation, instead of saying MIT or Caltech for their affiliations, they said LIGO-Virgo collaboration. And those had been the authors who had signed the paper. And I told you about the LIGO scientific collaboration. I'll tell you about the Virgo collaboration a bit later. Let me tell you a little bit about the other matters of this talk, which is just one slide. But this is that I am afraid that, and I am guilty, I was guilty of this, so I assume that you do too. When you think about physicists, you think of Einstein, and you probably think of this picture of Einstein. And you think about Nobel Prizes, and you probably think about people like Ray and Kip Thorne. And these are old people. But when they did their best work, they didn't look like that. They looked like this. They were young. People who do science, people who do the best science, the novel science, the important science, are for the most part young people. They were Ray and Kip in their 70s and 80s. That was Einstein in 1915, in 1905. That's when he did his best work. And when you think about the LIGO scientific collaboration, you might think about the few people that were on stage that time, but we are a lot of people, and these are mostly young people. And when you put a lot of people in there, then you lose sight of the individuals. But there's a lot of diversity in these individuals, and we need that diversity. It's not just geographical diversity. We have people from many different countries. It's age diversity. Actually, most of these people are young, so not old. Most of these people are young, and those are the ones who do the best work. But also lots of different expertises. We need engineers, we need physicists, we need technicians, we need the staff support, we need the janitorial support, we need everybody to be able to discover gravitational waves. And one picture I like is the people in my group. I was in Washington, but my group was celebrating in Louisiana, and these were them that September 11. And you can tell they don't look like I do. They are all young. Well, they are a few years older now. But anyway, the message is when you think about scientists, please don't, or physicists, don't think about Einstein. Try to imagine young people and try to meet those young people doing science. I was telling you about Virgo. The Virgo is another detector in Europe, a 3-kilometer detector in Europe, and that we collaborate with them since long before the discovery. In 2007, I think it's when we started taking data together with first-generation detectors. They also upgraded theirs to a second-generation detector, and we've been taking data with 3 detectors for several years now. There's also the LIGO scientific collaboration also operates a detector in Europe, in Germany, that's called GEO 600, which is a shorter detector, so it's not as sensitive. We use that especially to test new technologies. This quantum squeezing technology was tested first there. We are also now collaborating with the CAGRA collaboration. So now we call ourselves the LVK, LIGO Virgo CAGRA. That's in Japan, who operate a 3-kilometer underground detectors. And there's a project in India that I should not say planned because it's been approved. It's actually been funded with money, finally, after a long wait, but it's finally going on. It started, it acquired the land and it's going to begin building very soon. The money is all there now. So we are a big collaboration because we all work together instead of competing with each other. You might have heard that in physics, it's important to replicate experiments and replicate with different experiments, independent experiments. In our case, we do replicate. You saw Hanford and Livingston. We needed the 2 detectors to confirm that we had a gravitational wave, but we also need more than 2 detectors because we want to triangulate. And if you have only 2 detectors and you are asking, so that first signal that we saw, where does it come from? And with 2 detectors, you can say, well, it comes from there. And this is the localization we have for most of the gravitational waves that are detected with LIGO detectors, with the 2 US detectors. But there are 3 in here that are detected with LIGO Hanford, LIGO Livingston, and Virgo. And you can see that we can say it's coming from there. And astronomers say, well, that's still too big. But for us, it's a lot smaller than that, right? You need 3 detectors. We need to not compete, but analyze the data together. And that was very, very important in 2017. Does anybody here? Does anybody remember? Well, I know some people do. Does anybody not in LIGO remember 2017? It didn't get to the newspapers as big news as the one in 2015, but that's when we detected a very different signal. We had detected by then 10 black hole mergers. So that was the first one, and it's still the strongest one. I have to admit, that's very curious. But we had detected several others by 2017. But then we detected this. That was August 17, 2017. This is a lot longer. Notice that these are a fraction of a second, half a second, and these are more than 30 seconds. So this is a much longer signal. These objects are merging at a much higher frequency, which means that they are smaller. Smaller, like they could be neutron stars. That is our target. Maybe these were neutron stars. And that was amazing because at the same time, there was that's a sound of our signal. And this is a Fermi satellite. And less than 2 seconds after, 1.7 seconds after the merger of our signals, this was in their detector. Now, I'm not telling the story right like it was, and actually it was a faculty here at Penn State who can tell you the real story. Chad, who is sitting there. This was amazing because we are plotting this as a very clean signal, but it wasn't very clean when the computer saw it. There was a big glitch in here that broke down our system of automatic alerts. We had automatic alerts every time that the signal in Hanford and Livingston was there, or 2 detectors because we were taking data with Virgo. And because Virgo didn't see it, and although it had seen previous ones, and Hanford saw it, but Livingston didn't because of that big glitch, we didn't have the automatic alert. But Chad and people in his group all had signed up for receiving these alerts, and they said, well, that's very close. And they looked in the data and they saw it in Livingston too. So this was a merger. Why was it not in Virgo? Well, it turns out that the detectors have some blind directions. There are some directions for which the detectors are blind, and those are very thin directions. But because we knew we could see signals with Virgo, notice this is the one we're talking about, but this one was 3 days before, and this one was a day after. So 3 signals in a week. But this one we had seen 3 days before, and we had seen it in all 3 detectors. So we knew that Virgo was working and was working well. We had detected several things with them. So that meant that if Virgo didn't see this one, it wasn't that blind spot, which meant even better localization. So it was amazing good news that we could do it with all 3 detectors. This was this validated the so many discussions we had had about taking data with Virgo together rather than competing. It's a tribute to international collaboration. And because we could localize it, we could tell astronomers, go and look there. Without Virgo, we would have said, well, go look there or there, maybe. With Virgo, we could say, go and look there. The Fermi signal, the signal in gamma rays, was also localized, and it was consistent, but it wasn't such a good localization. But in there were 40 galaxies. So astronomers began looking at each galaxy in turn until in one galaxy, they discovered a bright spot that had not been there before. This was before, and that was then, and it was there changing colors. That bright spot disappeared in a couple of days. 10 days later, there were X-rays and radio waves coming from the same spot. Those waves lasted for a year. This was amazing. It was what we call now a multi-messenger observation. And we could tell the full story because now we had the gravitational wave signal, the gamma rays, the optical rays, the radio waves, the X-rays, and Hollywood, well, not Hollywood, but NASA, who's the Hollywood of science, made a movie about this. These are the neutron stars producing the gravitational waves. We're getting closer and closer together. They will merge and produce lots of gamma rays. Then this isotropic emission is going to travel and then produce a shock wave with the particles that are farther away. Those are the ones that took 10 days to get to, that produce the X-rays and the radio waves. And we have the full story. It was amazing. It is my favorite detection. Not the first one, because I had to work very, very hard, and I was very stressed about this one and that one, but this one was great. In fact, we can tell even the story on how elements in the bottom half of the periodic table are created, elements like gold, because those were assumed to be created in supernova explosions, but there aren't enough supernova explosions to explain the amount of gold on Earth and in the sun. You knew that there was gold in the sun? There is. We cannot go and pick it up, but it's there. But now that we know that neutron stars merge, because we have seen this merger, and we know from gamma ray bursts that we can assume that many of the gamma ray bursts that they see are also neutron star mergers, we can explain better how gold is produced. And that is what appeared in the newspapers, in some newspapers. Anyway, let me finish with a few slides on the present and the future. So we have the first time we took data with LIGO. We were analyzing the data with LIGO and Virgo, but it was a LIGO detector taking data. It was in the first observing run in 2015 and 16. This number is a distance to which we can observe neutron stars. And that just is a metric for how sensitive we are. So the bigger that number, the better. So this was our first observing run. This was our second observing run. Virgo joined us only for the month of August. And in that month, we saw those 2 black hole mergers and the neutron star merger. I mean, nature has been very, very lucky with us. We have worked very hard, but nature has been so lucky, so generous. The third observing run started in 2019. We finished in March 2020. We were going to take another month of data, but everybody knows March 2020 a lot of things happened around the world. So we stopped taking data. We were taking data with Virgo. We saw many discoveries. Kagra was beginning to take data, but not at a very good sensitivity. You see that number is much smaller. We took a long break. We were going to take a break, but the break was a lot longer for reasons that you can imagine. But we got back taking data last year. On our fourth observing run, we are now taking what we call a commissioning break, just a 1-month break. We're going to begin taking data in April again, and engineering run in March. So we are close to the second half. Virgo wasn't able to take data with us, but they will in the second part of this run. And we're going to take a break, and then we have even better, we expect to have even better sensitivity in the future. And these fonts are a bit small, but this goes to the end of the decade. So we started, this was our first detection 2015, but we have plans for the full decade and even farther away. In 0103, in these first 3 runs, not counting the last one, we produced a catalog with 90 different detections. I told you about that first one. I told you about that one, the neutron star merger, the first detection, but we've had a lot of black hole mergers. We've had only one other neutron star merger that we could not localize as well, and it was farther away, so there weren't multi-messenger signals from this one. We have detected some that are neutron star and black hole mergers. Each of these has 2 dots. Those are the 2 black holes merging into a bigger one. This has the record of the heaviest one, and these are so heavy that some people don't think that this could have been produced by a supernova explosion. So maybe this is a 2nd-generation merger. Maybe this black hole was already the merger of 2 other ones. We are just learning all of this. We have all of these. These are now more numerous than the X-ray black holes we knew about before our detectors. So we are doing black hole astronomy with gravitational wave astronomy. It's been amazing. And that was the 0103. You can go to LIGO.org to get more details. You can even get an app to get the charts because we have public alerts. And in 04, we have had, and I have to look at this number because I don't remember, it's 81 public alerts. So we have had 81 detections we are confident enough about. We had to have some retractions because these alerts are automatic, but then there are humans that go on there and say, no, that doesn't look like a detection. It looks like noise. My group in particular looks at decreasing the noise in the detectors because I'm very ashamed of those. So I don't like those retractions, but we do the best we can. Anyway, this is public. You can go there. You can go and look at the localization. You can see that sometimes we only have one detector seeing the signal. So now we don't look for a second one if we are very confident with one. Again, the group here at Penn State is the one that has the best, well, in my opinion, the best code for detecting these gravitational waves. And this is not the only way to detect gravitational waves. I told you about LIGO and Virgo and Kagra. They are all ground-based interferometers. Ground-based interferometers can detect signals, gravitational waves that have between 20, 30 hertz to a few kilohertz, and those are produced by these stellar mass black holes, tens of solar masses, many tens maybe, but not the big black holes that are at the center of the galaxy. At the center of our galaxy, there's a black hole that's 4 million solar masses. It doesn't have a companion black hole, but in some galaxies, there are 2 black holes. Some galaxies are colliding. Those are 2 black holes. And those black holes are so big that the waves they would produce, the gravitational waves, are a lower frequency. So for those, you need a much longer detector, and that's a space detector. And that's called LISA. That project is in the works, and it's led by the European Space Agency. If you want to look at the supermassive black holes, the billion solar mass black holes, then you need something even longer. I call this a galactic interferometer. We have neutron stars in our galaxy. We receive in radio telescopes the radio signals from those galaxies. So you can use those signals as if they were the lasers of an interferometer. And we can see those signals. I say we, I don't work in that collaboration, in that field. We as humans can see those. And I have news about those, let me tell you. This is the Nanograv collaboration. That's a North American nano, because these are nanohertz, very, very low frequency. And it was only last year, in July of 2023, that Nanograv, but also the Australian Pulsar Parkes Pulsar Time Array, and the European Pulsar Time Array in collaboration with an Indian collaboration, and the Chinese Pulsar Time Array, all of these collaborations were not collaborating with each other. They are actually going to put their data together, but they agreed to publish at the same time evidence for the first detection of these signals from supermassive black holes. In fact, they don't know what the origin is. That's what they suspect it is, but it's not like a like the merger I showed you before. It's more like a hum, because it's happening all the time. These are signals that are coming from many, many different mergers all over the sky, well, the universe. So they all arrive like a noise, a background noise. And this is what how they sing it. I love that video. It's a big collaboration too. Those are some of the members of the collaboration. About LISA, I told you that it was led by the European Space Agency, and it was only a couple of weeks ago, January 25th, well, a month ago now, that they approved it finally. It had been in the books. It had passed several stages to be approved, but finally it's really going to launch in 2035. We have to be patient, but it's going to get there. And for ground-based observatories, we are not done. We have plans for third-generation detectors. And these detectors would be longer detectors. And this is, again, something that Penn State is very involved in. Satya is one of the people, one of the principal investigators of this project, the Cosmic Explorer. That would be a detector that would be 40 kilometers long. So this is only in the conceptual stages now. National Science Foundation is looking at this carefully to see if whether or when they can fund it. There is another concept in Europe that's called the Einstein telescope, which would be a triangular 10-kilometer detector. This would detect all the black hole mergers in the universe, even those that happened very, very early on, maybe primordial black holes that were not created by supernovas. That is amazing. We would see these neutron star mergers with such a high amplitude that we could detect those signals that make the gold. We would really get the fine details. So that's where we're going, or that's where we want to go, with your help, because again, this is all taxpayers' money. It's all your money. So I hope you like this and you like and agree with me that this is just the beginning. There's so much more coming. Thank you.